In SAC 103, we've got a conservation of energy problem involving a spring. We've got an ideal massless spring, spring constant K, and unstretched, uncompressed length L0. Person comes along and puts a block on it, where the block has mass M, and they press down on the spring with the block until the length of that spring is just L. Then they release the block rather suddenly. This block goes flying into the air, and they want to know how high is it when it's at its highest point. How high above the floor? Let's call that y prime. And therein lies the question, what's it equal to? Where our spring is out of the picture by that time. It's unstretched and uncompressed again. So I'm going to call, we got a conservation of energy problem. You got to draw a good before and after picture. I'm going to call this one the before picture. And the person releases it. That's the instant of release right there, before it's gone anywhere. They've released it, now it goes flying up in the air, and this will be the after picture. Where in the after picture, the spring is no longer relevant. It's not touching the mass. No more energy stored in that massless spring. And let's try writing the energy before is equal to the energy after. Break that up into kinetic energy plus, I got potential energy stored in the spring plus gravitational potential energy. Those are all the kinds of energy that I can have here. That's a big U there. And put primes on all those. And then recognize there's no spring potential energy in the after picture. In the before picture, it's got zero velocity, so it's got no energy of motion. And in fact, in the after picture, it's at its highest point, where just for an instance there, the object has no velocity, so it's got no kinetic energy in the after picture as well. We do have gravitational potential energy. It's up high above the floor in the before picture and in the after picture. I'm going to define the floor level to be my reference level, mainly because I want to know at how high above the floor is it. So what's its height relative to the floor in the after picture. So in the before picture, we're going to have a 1/2 kx squared. That's our expression for spring potential energy, plus an mg, let's call it y for the moment. And that's going to be equal to gravitational potential in the after picture is just mg y prime. Okay, we're solving for y prime, but we're supposed to use symbols that are given in this problem, such as L, L0, and known quantities as well, such as G. And hopefully we're given the mass of that block. Yep, there's the mass. I got M, I got L0, and L. And of course it's okay to use the gravitational constant G. That gravitational force constant for the near the surface of the Earth positions. Okay, well, X is not one of those unknowns, so X by definition represents the amount by which the spring is stretched or compressed. In this case, it's compressed. By how much is it compressed? Well, it'll be this distance right here from its compressed length to its uncompressed length. This is X. And we can see, well, if I went up a distance L plus X, I have L0. In other words, X is just L0 minus L. So let's go ahead and take advantage of that. It's 1/2 kx squared. In terms of known quantities, I think they gave us k as well. Yeah, there it is. So it's okay to have a k in our answer. 1/2 k times L0 minus L, all squared, plus M was given, G is a known constant, and then Y in this picture is just L. Y and L are the exact same distance. I'm going to use the fiducial mark on the bottom of the block there for convenience. And this becomes MGL, and that's MGY prime, where Y prime is what we're looking for. So Y prime, I'm switching sides, and I'm going to divide both sides by MG. It'll be K over 2mg. There's the 2, and then I'm dividing both sides by mg times the L0 minus L squared minus L squared, and then plus L. And that'll be our final height of the block. Might be some concern about the fact that I was measuring the height of the block using the bottom of the block. Note that if the block raises, if the bottom of the block raises a distance y prime minus L, which is what it does subsequent to release, then so does the center of mass. So the change in the distance that the center of mass is above the reference level is the same. Another way you could have looked at that is include half the height of the block up here for the position of the center of mass to determine what I mean by y, but then have our reference for gravitational potential energy also be a half of the block height above where I've indicated it, above the floor, and we get the same exact answer no matter what. But it should be recognized here that there is some interpretation of the answer. What I mean by y prime is the height that the bottom of the block is above the floor in the after picture. And this is our answer. And that wraps up SAC 103, problem number 1.